All right, good morning. Let's get started. Welcome to lecture 2 of 251B. A few things to mention early on is that the assignment 1, which is essentially the lab 1, is posted this week. There will be a detailed guidance tomorrow in tomorrow's discussion, so please do attend that. What I'll do in this lecture is try to outline why are we doing this kind of a lab and how should it help you. But the TA will walk you through the steps, step by step, that need to be done, and then you get to do it by yourself. It shouldn't take very long, so we would like you to complete it by the end of the next week. It is one of the important elements for a project, if you would like to put your project in a context of a complete system. I wanted to give a little bit of an update about the project. So this semester we are essentially offering you to pursue your own projects. Some have asked, can I do something that is related to my research? Of course, but we don't just want you to do, to send us your research project report, a chapter of your master's thesis or something like that. We would like you can pick a related topic or topic that is a part of your research and then explore it deeply. Or a part of your capstone project would also be a great thing. But we do want to have essentially this two-phase study where the midterm report will be a study of the state of the art, where you would describe the state of the art, make sure that you clearly understand it by picking, say, 5 relevant papers from the field, and then writing a summary of that. One important thing, that summary should not be just basically quoting verbatim what each of the papers said. Paper 1 presents this, paper 2 presents this, paper 3 presents this, paper 4 presents this, paper 5 presents that. No, it should be, here is what is the problem. Here are the possible solutions. Here are the metrics, how we evaluate these solutions. Here is where these solutions stack up. Here is what they do well. Here are their shortcomings. We propose to either experimentally evaluate which one of them is the best, or we came up with an idea to come up with a better solution, and that's what we're going to evaluate in our final project. The final project would essentially be an experimental evaluation. In that experimental evaluation, there can be a whole bunch of things that you can pursue. For example, they can be projects that are a building block, or you can try to build a complete system. It would be a great idea if you can, at least if you're designing a small block, you can put it in a perspective of a system. We also get questions occasionally, can I do an analog project? No, this is a digital circuits and systems class. However, we have had really nice projects in the past where people have done digital circuits that perform a traditionally an analog function, like all digital frequency synthesizers have been popular. Digital PLLs have been popular. Designing drope detectors based on digital circuits to perform drope detections, the supply drope detection, have been good topics too. Or anything else. We have had crypto circuits. We have had hardware security. We have had memory studies. Anything is good. Do you have any questions about this? And I will definitely have more details, and we'll guide you. All three of us will guide you as we move through the semester. Any questions for now? One question that you may have is, how do you find these papers? Ask us for help. I mean, that's what the office hours are for. And they're on, generally, you'll find them in IEEE Explore, and start from the top conferences in the field, say ISSCC and VLSI and General Solid State Circuits, and you'll find something there. And then go from there. Somebody posted a question, and I'll respond to that. In order to access IEEE Explore, you need to go through VPN to campus. That's how Berkeley subscription works. Okay, moving on. I gave you a few papers to read. The first one is what we're going to cover today. This is our work that describes this chipyard framework that we have been using for designing SoCs. And that's what I'm going to cover, walk through today, and you're going to see some examples tomorrow in the discussion. And then a few weeks later, we are going to cover some of these transistor models. There is the NARS paper, which I think it's a matter of general education to read. So at least read the first part of the paper that covers the scaling principles. You should know that one fairly well. The second part is about fabrication, and that is well obsolete. You can jump that. You can jump through. You can skip that. But then at some point in the class, in about 2 weeks, we'll spend some time on modeling transistors. And there are 3 models, transistor models that come in very handy, and they're listed over here: Sodini, Cohen, Moll, Toko, and Meyer, and Sakurai and Newton. Those, although they're fairly dated, they're all relevant, and they're a part of that story that I've said that when things are changing, technologies are changing, but some of the basic behavior of the devices is not. So these models are essentially governing the IV characteristics of velocity saturated transistors, and are applicable to anything from planar devices, from somewhere sub-micron down to FinFETs and FDSOI. There is another set of models, EKV models, that are used in computer simulations, but they're not. And there is some of you might have encountered that in analog design, and some of our colleagues have switched to teaching analog design by using those models. But they don't give us the intuition that we wanted to have out of these models. The first 2 Sodini and Toh papers essentially lay a foundation of the BSIM model that has been in use for many years, and it's very handy for hand analysis. The third one, Sakurai and Newton, is the alpha power law model, which is very helpful for analyzing block level delays and power. Okay. Any questions about that? Okay, so as you can probably hear, my voice may or may not last the whole lecture. but if it does, I'll take some breaks along the way. What I'll cover today is the concept of a system on a chip generator, which in this case is called Chipyard. It is something that we have developed in research here, and is being used in education. So you may encounter it in different classes. You'll encounter it in this class, but you might encounter it in some pieces of it. And if you take architecture classes, and you've actually seen a little bit of that in 251A already. So because some of our design flow is being covered by Chipyard. Before we get into that, let's talk a little bit about RISC-V processors and RISC-V processor cores that we have. So by now, since 151 or 251A is a prerequisite, everybody has seen a RISC-V core and has perhaps designed their own. We have designed 2 or 3 three-stage RISC-V cores, but in other classes, say in 61C, we have also seen a 5-stage pipelined version of the integer core arbitrary2i. One thing to keep in mind is that 5-stage processors, 5-stage in-order processors are the workhorse of the industry. If you look at what is out there, some very large percentage of processors that are being used are 5-stage pipelines. That's what, although when you think of processors, you're thinking of some high-performance designs that are coming from Apple or Intel that have deeper pipelines and out-of-order execution, but majority of the things that are sitting in our Wi-Fi storage devices and so on are essentially 5- and 6-stage in-order pipelines. They're doing all kinds of day-to-day jobs. So many of the projects, if you're doing any kind of an embedded project, a good idea is to start with a 5-stage core and see if it suits our needs. Many other bigger processors will generally be overkills. Small microcontrollers are using 2- or 3-stage pipelines, but that's generally insufficient for many of the applications. In order to build a full system, we do know that just the core itself is not going to do much. We need to replace this IMEM and DMEM with real memory. And that may be either a scratch pad if it is an embedded core, or a full-blown cache that links to the memory system. We may need some kind of coprocessors. Often we'll find at least a IEEE floating point coprocessor and some peripherals. But in general, when we're building system on a chip, we'll need more. One of the things that many of you might have encountered, you've learned, is that figuring out this forwarding logic and things that go along with bypassing the pipeline stages is tricky. And if you have an error in your design, it is often associated with the forwarding logic. We do, you certainly can take your own project, core that you've designed in the project, but we know that some of them had bugs. So going forward, we would like you to just use a provided, well-tested core. In this case, it is a Rocket core. That was the first core that was designed for RISC-V. And one thing that characterizes it is not just a single instance of a core, it is something that is so-called generator. We're going to encounter these concepts of generators a few times in this course. A generator is essentially, they are written as a software program, software that essentially writes out an RTL for a particular instance that we can parameterize. So this, does not generate all kinds of random cores. It always generates in order single issue 64-bit core. It is possible to configure it as a 32-bit core if you like. Its parameterization enables it to turn on or turn off floating point unit. It has some other features here that that RV64GC. G is general, meaning supports integer, floating point, and multiply atomics as well. C is compressed. It supports the compressed instruction set, which is important for many of the embedded applications and simply means that the core can run any code that is out there. One thing to notice, there are many, since RISC-V is completely open and free, IC specification, anybody can write the core, not just us in the classes, people do that in industry and provide commercial cores out there as well as open source cores. Many of these that you can find or typically were able to find out in the wild did not have a correct implementation of the compressed instructions. So that's like scarier than implementing the bypassing logic. It has a physical memory protection, pieces of a protected spec, can support supervisor ISA and virtual memory, which means that it can boot Linux. When you look at the number of cores that are out there, there are very many of them, but very few that are in open source are capable of booting an operating system, a modern operating system. The way how we hook up coprocessors, as we are going to exercise in the second lab, is by using so-called rocket chip coprocessor interface, or ROC. So you can put any coprocessor in there that you like crypto or floating point or machine learning and so on. So we'll have a lab that will where you will design a simple coprocessor and attach it. And to support the memory system, complete memory system, it has caches and starts with level 1 caches, which can be configured. Essentially, you can terminate in the first layer of memory if you configure them as scratch pads and they're not backed by the outer memory system. Now, what is inside the rocket is, essentially something that is very similar to what you'll kind of find in your class projects that you've designed, but it has a little bit more in there. So if we look at it, so I can annotate over here. You can look at it divided into the front end, the execution and completion stage. In the front end, it has a branch predictor, of moderate complexity that you will find over here. That it has a branch table, branch history table, and predicts with reasonable accuracy where the branches are, whether the branches are going to be taken or not. So that's perhaps, although some have done branch predictors to improve the performance of their 251A cores, this is a more sophisticated design than that. So it can take PC++, or a predicted target. Then it goes into, you know, the rest of the fetch is essentially essentially set up as to support virtual memory systems. So there is a TLB in there and a tag comparison. One thing to keep in mind is our students or students who have designed Rocket have been pretty terrible at documenting. They actually never drew the diagram. They just open sourced the chisel generator. And some other people have been a lot better in documenting this. So this documentation for the Rocket, although slightly dated, does come from Cambridge University. Core pipeline is something that essentially is what we have seen before, what has been designed in a class, except that it does have a synthesized multiply division unit and ability to hook up a floating point unit. One thing to keep in mind, the floating point unit is has been designed. For example, we have had grad students in the past design floating point units, and getting them to be standards compliant is really difficult. This floating point was written by the person who have actually written the standard, so we believe that it faithfully implements the standard and nobody is complaining about that. So it goes through the remaining 4 stages of the core pipeline. There should be no surprises here. Then there is a data cache that is fairly sophisticated. It can be configured to be write through or write back. Probably evolved version of what people have done in 251A project. But this is basically given to you. Complete design is out there for use, and you can configure it in the way you like and run with it. And Rocket has been used in many research chips, not just in Berkeley, in other places, but chips. There have been a number of products that have been derived from Rocket, and people say that it is in hundreds of commercial sockets. So it's a good processor. No need to mess with that. Now, to actually build an SoC, we do need a processor core. And Rocket is a good one. It meets 90% of the world's needs as a 5-stage core. There are things that are missing compared to some commercial cores, and especially in the debug space and so on. But that's okay. It should not stop you from completing class projects. We do have other cores, and you're more than welcome to, if that is something that you're interested in. There is a Berkeley out of order machine that's also a generator of high performance cores. There are some others that are in development. If any of you are involved in that, we are more than happy to have a project related to exploring something like power performance, area optimization of any of these cores. Besides the cores, it needs to have a memory system, and in this case, Rocket chip generator just had a generator of L1 cache. The L2 cache generator was added a bit later, and had a coherence protocol. And it's a really elegantly written generator, very much worth looking into if you are into that. To be able to connect multiple processor cores or other devices on the chip, it needs to have some kind of a system level interconnect, or multiple ways of interconnecting things. In RISC-V world, that is TileLink or TileLink 2. And then once you have all of that, you can design custom blocks that will make that SoC be application specific for, say, communication by adding Wi-Fi, Bluetooth, and that kind of connectivity, or Ethernet, and so on, or imaging, etc. And then another really important and kind of annoying thing is that every SoC does need to have a bunch of peripheral devices that are used for communicating with with the rest of the world. So JTAG for debug interfaces, serial to parallel, I2C. If we said we can boot operating systems, well, it needs to have the first stage of a bootloader in the boot ROM, and so on. All of this does show up in the rocket chip generator. So that leads us into a discussion of Chipyard, that is an SoC generator that is based on the rocket core and the rocket chip generator. I'll pause here primarily to let you ask any questions you may have so far, but also to rest my voice. Okay. Let's move forward. One thing that has dramatically changed in industry and education over the past, say, 10 years is the emergence of open source hardware. And I've referred to it early on in this lecture, saying that there are a lot of RISC-V cores out there. So what's up with open source versus commercial closed source? Traditionally, a lot of hardware over the past couple of decades has been kept tight under commercial licenses. So you have a choice: either design everything from scratch yourself, or you can buy a piece of IP, intellectual property, that does a particular function that you need there. So when you're starting an SoC project, some people have quoted that these licenses, just to try things out, to build a prototype, would cost millions to tens of millions of dollars in license fees for, say, processor cores, memory interfaces, memory controllers. Many of these little peripherals cost something. They're not free, although they any of us can design them, but they're trusted and proven, and you don't want to mess up your chip by a simple mistake somewhere in a peripheral unit. So people have realized that is really dragging the industry down. Software industry has really flourished when much of it became open source, so people can commoditize these commodity items and build their differentiated stuff on top. The true revolution really in open source hardware happened with the RISC-V ISA. It appeared that the ISA essentially, all ISAs before that were closed or not really open, and Berkeley came up with the idea that instruction set architecture does not really have a ton of proprietary stuff, and we can design one and open it. The idea was to use it for classes like this one. Before that, like 61C and 152 and 151, but it turned out that the design was pretty good, and commercial people started picking it up. So these open source and closed source implementations of RISC-V cores have showed up, and that is one of the first things that enabled building the complete systems. Without the cores, it's really hard. I mean, if you have to license that, other things don't really help too much. The other thing that came came along is this need to try to meet many needs. And expressing things as generators in Verilog has been difficult. It's not easy. We have seen generate command in Verilog, but that's not really it. So the language which came along, that is called Chisel, came out of Berkeley as well, which is one of the ways of expressing generators, so writing generators. We'll have a lecture dedicated to Chisel next week. Chisel has so-called its intermediate representation called FERFL, does not immediately translate to Verilog, it translates to intermediate representation, like many software frameworks, and we'll see some of the FERFL as well. RISC-V showed up. Some of you might have encountered BAG. Then we have Boom Core, we have a Rocket Core, they're out there. There is a number of accelerators. If you've taken 152, 252, they might have made you write an accelerator, like we're going to make you do that here. Or if somebody has taken CS250, the class that predated this one, they typically would write accelerators for that. So there was a whole bunch of accelerators. You just go through GitHub and you'll find very many of them. And caches came with the Rocket, and they've been added. L2 caches were added by Sci5 in the open source. There is TileLink. There's Diplomacy, which is a protocol that connects things to TileLink. There is a number of peripherals that are out there that I've mentioned before. There is a configuration system. We'll mention Hammer. This is our physical design tool that you actually have been exposed to in 151. You know, there are ways to simulate things. Some of you might have heard of FireSim. And when you took a look at all of that, there are these open components, but none of them really worked with the other. I mean, they actually might have worked at some point of time in the past if you found the right version of the source code and the right version of the tools. You could have gotten it to work, but it became apparent that this ecosystem of open source things has become really big and hard to manage, to the point that our grad students, people who were in your shoes about 3 years ago, started trying to start their own projects around this time, and could not get anything to fit with another Mac to work with anything else. And this silly communication kept going, and which version of the tool do I need for this accelerator to hook up to that version of the RISC-V core? And there were these hard-coded recipes. You pick this from this date or this hash, and that from this with this hash, and then put them together, and if you get the right version of the tool, it might work. So the goal here was to enable research and education, is to put this into a generator that can make complete SoCs. And that's how Chipyard came along. So Chipyard organized all of these open source components into tooling, rocket chip components, and methods for putting things together in the rocket chip and design flows. One thing to keep in mind, Chipyard typically lags. What you will find in Chipyard lags by a few months, 3 to 6 months, any of the components that are in there. So it may not be always based on the latest version of Chisel or FERFL. It may not be implementing the latest and greatest updates to Rocket and Boom cores, or the cutting edge development in a machine learning accelerator, but all of them work. And if there is something that is really pressing, there is a bug in any of these components, it relatively quickly, Chipyard gets bumped. Another important thing, so tools are part of that, not just the components, and the design flows are being tested that they can build at least a basic SoC with that. I mentioned FireSim. That is a way, and I'll have a slide on that. That's a way to use cloud FPGAs to simulate larger systems. There is Hammer, which we have seen. This is our flow tool that we'll explore deeply in Lab 3. That essentially does synthesis, place and route, and everything else that needs to be done with that to make a layout. And there is software RTL simulation that can be performed. BAG, Berkeley Analog Generator, has been in the plans to add to this, to have a more systematic way of adding analog components, but that's still pending work. So one thing that I have mentioned but haven't really gone into details is what is rocket chip? I mentioned the rocket core. What is a rocket chip? Rocket chip was the first attempt to build an SoC or a part of an SoC by taking a rocket core and adding standard peripherals around it. So it is inside the chipyard, and it's a highly parameterizable SoC generator. It comes packaged with a default rocket core, but you can add your own core. There are a few that are verified to work, but you're more than welcome to add a different one. It has a standard ROC socket, so you can add your own coprocessor or pick one of those that exist from, that have been approved by research groups or product of somebody's 252 class project, if you like. Or you can add peripheral devices that are not in the coherent space to the Encore. We have found that even if you're doing an analog project, it's incredibly convenient to have a small processor. I mean, if you have large enough of a die, it's incredibly convenient to have a small processor on your chip, so that you can talk to it through standard protocols. And if you're testing an A to D, it's really handy to have a processor with a memory on it, instead of writing some really intricate scan chains and manipulating them from the outside. The other component of a rocket chip is a library of reusable SoC components that can be added. So there are memory protocol converters, so it converts from tiling to AXI, various versions of AXI. There are arbiters and crossbar generators for on-chip interconnect, and automatically builds clock crossings and asynchronous queues. We have mentioned Chisel, and it is the largest open source Chisel code base with tens of thousands of lines of code. It was developed by Berkeley, but it quickly became impossible for our graduate students and one staff engineer to maintain it. So it has been maintained by many. So it is out in the open source, and if you look at it, well, it's not as big as Linux, but it's maintained like Linux. It is nominally hosted by an open source alliance, industry alliance that we are a part of, which is called the CHIPS Alliance. Most of the maintenance comes from Sci-5, which is a startup that came out of Berkeley that was founded by the people who designed the original RISC-V spec and the rocket chip. And we have some minor contributions to it at the moment. In practice, Sci-5's Freedom E310, one of their first chips, was based on the rocket. So to dive a bit deeper into that, what we will find inside of a rocket chip are few of the standard components that enable us to build an SoC. The building blocks, processing building blocks are so-called tiles. And they're units of replication for a core. What you will find there is a CPU. By default, it's Rocket, or you can put a boom. We also have ability to use some other people. We incorporated some other people's cores, like Ariane, which is now called CBA6 from ETH Zurich, and so on. And if the core is correctly designed, anybody can drop it in. Any of you, if you're interested in adding different cores, I mean, we have had requests for Alibaba's cores and so on. We don't have time to maintain all of that, but if anybody would like to do that, more than welcome. They're more than welcome. There are L1 caches that are a part of a tile, and a page table walker that enables implementation of the outer memory system. L2 cache has been contributed by Sci5, and that's a big help that enables us to build these cache coherent multiprocessors. Front bus connects to, say, DMA AXI devices. There is a control bus that connects to core complex devices like a boot ROM, platform level interrupt, or core level interrupts, and the debug via JTAG. So these things you don't have to, in general, you don't have to worry about. If it works on Sci5's chip, it's highly likely it's going to work on our chip. Some of you might have found out some quirkiness about that, but in general, these kinds of things work. And if something is broken, open source community is pretty good at figuring out that it is broken. There is a periphery bus where we can use for connecting peripheral devices like AXI, and there is a system bus that essentially will connect this hierarchy of buses together. There are ways. So one thing that I mentioned, and maybe of interest to some of you to explore as a class project, is the Berkeley out of order machine, which is a super scalar out of order core that is open source, designed in Chisel as a parameterized generator, and can be designed as a small out of order core to like mega version that looks like a Xeon. And in simulation has a great performance, but its implementation is really tricky. It's hard to get performance, meaning that by using design flows that we use in this class, Boom will probably run at about a gigahertz, maybe a little above a gigahertz. And then somehow you look at these things that Intel or Apple and Qualcomm are building, and they run at 2.5 or 3 or 5 gigahertz, and some magic happens over there essentially in the physical implementation. We'll talk a little bit more about that in this class, but we can have a boom core dropped into the system. What is inside of a boom core? It's also a three-way. You can view it as three parts. It having 3 parts. It has a front end that fetches instructions and predicts branches. Now, the branch predictor is a lot more complicated in Boom and has much higher performance. It is similar to what you'll find in a high-end processor, but it is also a lot bigger. And if you look at how commercial cores have been evolving over the past decade or so, branch prediction has been getting really big. Again, you can configure it to be big. The challenge is you can configure RTL to be big. The challenge is to actually implement it. Then There is an execute with a configurable number of execution units that can be integer or floating point. There is a distributed scheduler that schedules these instructions based on what is open in each of the queues. And then finally, there is a load store unit that where these instructions, once where they retire, they get reordered and written back into the memory. There is a question in the chat. Yeah, what is the page table walker for that is used for supporting virtual memory? If there is a cache miss, the data needs to be gotten from the outer memory. And these page table walkers can be implemented in software or in hardware. I think we mentioned that in like in 61C. Rocket has a hardware page table walker like most of the modern processors. So does Boom. When you look at what is Boom, this is one of mega configurations. It kind of looks like what you will find in Intel Sandy Bridge or in ARM A76. Again, architecturally, it looks similar. The devil is in the details. Perhaps the branch predictors are not as accurate as you'll find in these high-end commercial processors. Also, we don't have an implementation that will achieve the performance of these cores, but you can totally play with them. One way, what we're going to see next week is to enhance performance of a system on a chip is to add an accelerator to the general purpose core. So that is done through so-called Rocket Chip Coprocessor or ROC. And there is a particular part of the RISC-V instruction space that is reserved for custom extensions. So there are particular opcodes that are reserved for something that is custom, that is not specified in the ISA. So you can do that. And essentially, ROC will take the instruction and communicate with the core. Will be coupled to L1 data cache, but also has a way to connect to the L2 cache. There is a number of accelerators that there exist that you can play with, like vector accelerators, memcopy accelerators, machine learning accelerators like Gemini is our own, or NVIDIA is open source, NVDLA. And there is a part of a tutorial that does that. There is a Java garbage collection accelerator, and as a part of your lab 2, I believe we'll be integrating a SHA-3 accelerator. One that is, has been very popular lately in the community because everybody does care about machine learning is this machine learning accelerator Gemini, which is a well-designed systolic array-based accelerator for matrix operations. There are lots of things that can be configured in there. And thanks to having Sophia as a faculty member who really knows machine learning workloads, it does execute a number of standard machine learning workloads well. Not just one, but a good range of them, good part of like MLPerf space in both inference and parser training. So those of you who are interested in this, we have had definitely class projects in the past where people have tried different kinds of things with matrix accelerators, and they used a core of a Gemini for experimentation. We have a vector accelerator that is a standard vector unit. If you're taking 152 or if you're taking 152, you'll hear quite a bit about it. One thing to watch out is the RISC-V vector spec has been just adopted this year after a long laborious negotiations, and this is not an implementation of RISC-V vectors. Berkeley may come up with an open source subset of RISC-V vector extension. Maybe in a few months, we'll see. There are no open source correct implementations of RISC-V vector extension at the moment. There are commercial proprietary ones out there, but somebody will write an open one, I'm pretty sure. L2 cache and the memory system is a multi-bank shared L2 cache, which is directory based. Sci5 has open sourced it. We are very thankful to them. It is fully coherent, and you can configure a lot of stuff in it, like size, associativity, and so on. And then it can convert at the end to AXI4 to hook up to a DRAM controller. We don't have an integrated DRAM controller, but there are some nice people out there on the internet that do have DRAM controllers. And if any of you are interested in connecting a DRAM controller, they'll work. Core complex devices are the standard peripheral devices that are needed in every chip, like to have a debug unit to support interrupts to a priority, and to have something to start booting the chip, like the boot room. Boot ROM is the first stage bootloader and builds the device tree for Linux and other operating systems. There is a programmable, there is a platform level interrupt controller, there is a core level interrupt controller, and there are built-in timers in there, and there are debug units. There is a number of other blocks. So there is I've mentioned this one before, there is a hardware floating point unit that is called a hard float. There is IceNet, that is a custom NIC for FireSim simulations that is slightly deprecated at the moment. And there is a number of Sci5 blocks that you can include, like GPIOs, serial to parallel, or UARTs to talk to an external model. And there is some Berkeley specific utilities that our grad students use for testing and bring up. There is an educational accelerator that you are going to be intimately familiar with from next week. So, any questions here? All right, I'll break for a second here. I need to refresh I need to give my voice a bit of a rest. I'll continue in about 2 minutes. All right. Oops. You guys hear me?
Yep.
All right, thanks. So let's see if my voice is going to hold on for another 25 minutes. Yeah, I told you, every time I get a virus, no matter what kind of it, if it is strong enough, it basically knocks out my voice the week after, and I have to do 3 lectures plus some other talking this week, and that's really not helping. Okay. So when you look at this, when you look at what is, how you can customize it, you can build it like the really minimalistic. So this one over here is the minimalistic, which is like a control core or a power management unit. In our chips, we have used this as a power management unit, where it is like the 64-bit or 32-bit version with a minimum amount of data and instruction cache. That's essentially a configuration that has been also used in a tape-out class and has been used in many projects where there is an analog peripheral that is over there, and you use the processor to control that analog peripheral. Maybe I'm using a word peripheral here, but if you're an analog designer, that's your dissertation in there. That and it's highly valuable to you, but it's a peripheral unit to a processor. So you can build more complex configurations that are shown in this picture. One on the bottom is a heterogeneous SoC that has a rocket tile, a boom tile. One of them has a vector coprocessor. The other one has a systolic array coprocessor. And that is essentially something that we have taped out 2 years ago and had a paper out of it. That was our, this configuration is on the bottom of the picture is essentially what we had in the paper that was generated out of Chipyard. And that's also, something like that is what some students may be doing this year as a part of a tape-out class exercise. So I'll just walk through an example, and you're going to see a lot better and much more intuitive way how we set up how we customize the chipyard to configure the rocket chip and then run the simulations with it. In many of these cases, you can just use pre-built stuff. And the way how you do that, you start with a top-level test harness. Test harness is on the very top that instantiates some of the basic tests. So you're going to do a class in Scala of my custom configuration that extends the configuration that is over there, that is based on a rocket chip with a base configuration. At some point, we are going to have you're going to play with this without really knowing the syntax for Chisel or Scala, but we're going to have a lecture on that and another lab where we will get some familiarity with that. Again, our intent is not to become experts. Some of you will just use this as a tool. Some of them will become much more intimately familiar if your research is tied to this, or your dissertations and master's thesis are tied to it. Then you can pick one of the standard configurations that will say this is with normal boom rocket top. So this will add things that are needed for boom, which are some system bus and a memory bus. And then these cores appear in one line. It says, let's add boom system with n boom cores, where n is equal to 3, and 3 boom cores show up. Then you can configure them to be large booms, which are in this way have a three-way issue. And then you can add inclusive cache that basically drops in that cache that I mentioned from Sci5 that has 1024 bytes, 1 megabit worth of cache. Then you can add a coprocessor here, which is a vector coprocessor Hwacha to all 3 cores, add a boot ROM, add GPIOs, and add the block device to simulate the outer memory and hook to simulation for the AXI memory. Remember, we don't have a DRAM interface, and specify how big is the outer memory. So that's it. Now you can take this and simulate it and see how well does it match your workload or what you're trying to do with it. You may decide that you will do something different, and the core 1, we can replace it with a rocket chip instead of a boom. We can decide that we can replace the accelerators. We don't want to have a Hwacha on every single one of them, and with simple 3 lines, we can put in Gemini, which is our systolic array machine learning accelerator, and a SHA-3, which is a part of the exercise that you'll eventually do. Then we can realize that Gemini really does not need a 64-bit rocket core. It can be replaced with a 32-bit rocket core. And we can say, in order to complete our system, maybe this just matches our workload really well, add the JTAG to it. Then we figure out that this thing is pretty big and we need to run it at different, run it from different clocks with different perhaps frequency and with decoupled interfaces. So we'll say that they have different clocks, and it will just add decoupled interfaces to them. Again, it does not drop in PLLs. You will need to do that if you like. Moving forward, we can simulate this in FireSim. FireSim is an FPGA accelerated simulation based on the Amazon EC2 FPGA instances that are on AWS. It was designed for essentially architecture research of data center like clusters, but has been mostly used for verification and validation of design of our designs and industrial designs as well that are out there. 6 or 7 companies do use FireSim for simulation because it is relatively inexpensive and a way to access quite a few large FPGAs for small amounts of money. In our case, it's relatively, it's free. So we supply our source RTL, any other, our SoC RTL, our custom accelerators, if you like, in Verilog or Chisel, add other things, network topology, software models, and provide the code to run, and then FireSim automatically makes it all work. There are a few things that have been tested, and like data center computers with thousands of SoCs. Another part of Chipyard is a tool called Hammer, which is a modular VLSI flow that is slightly different than what you will find in industry. So industry builds chips, builds a lot of chips, and perhaps does it with higher performance than what we do. But typically, when they commit to product or a project, you know, there is a big team that is associated with that, with tens or hundreds of people. And they have a CAD team or a design flow team that builds a design flow that optimizes the tools for that technology and that particular product, because this is something that's going to make a lot of money, so they better get the maximum out of it. We don't do that. In research and in teaching, we are more of a scavenger types. We will use any silicon area that is given to us at zero cost or at low cost. So we jump from a technology to a technology. We use any tools that they allow us to use, and sometimes we have had unpleasant situations where a CAD company would say, "Nope, we're not going to give you that particular license that you would like to have." So we need to jump to another vendor. So our objective has been to build a VLSI flow that allows reusability of components. So it's a framework written in Python, mostly Python, that uses the APIs into tools to build something generic. So you have methods that you would like to implement, and by using plugins for tools and technologies, it builds this program that outputs a customized Tcl script. And Tcl is a language that also originates from Berkeley, but back from like 80s or early 90s, that all CAD tools speak. However, almost none of our students are familiar with Tcl because it's a pretty old scripted scripting language. How many of you do know Tcl? Any raise of hands here? Not many. Before Python, there used to be Perl. Before Perl, there used to be Tcl. That's how it all it is. And I'm of a Perl generation. So essentially, Hammer is a high performance flow, but it is, you know, its emphasis is on modularity than achieve, you know, as opposed to achieving the highest possible density that is out there, such that we can use it for all kinds of projects and all kinds of technologies and tools. At the end, what you'll see is once when you have your custom SoC configuration described in RTL, you go through the RTL generators that support, you know, that targets RTL generators with a particular configuration will generate your RISC-V cores, your accelerators, your multi-level caches and peripherals, and then you got your RTL. That RTL can be massaged, and you're going to see in the next lecture a little bit about the FERPL intermediate representation, where you can transform that like lots of people do with standard software code, linting and stuff like that. But here there are, you know, many more things that we would like to do at the hardware level. You know, we would like to decouple parts of a block. We would like to replace memories with actual memories that correspond to what we'll find in FPGAs or ASICs, and different ASIC technologies may have a very different ways of treating those. Or we can just take that FERPL IR and simulate it as behavioral Verilog. So we have three targets: FireSim Verilog, behavioral Verilog, or VLSI Verilog. In this class, we'll mostly go for Hammer, but if any of you are interested in exploring FireSim FPGA accelerated simulation, that can be arranged as well. And doing software RTL simulation is relatively straightforward. One really important thing that people forget once they are they build their hardware is they generally need some kind of a software to run with it. And the beauty of RISC-V is that if you have your cores that are implementing the spec, then all the software works. All the software that is out there in a wild world from Linux and all the Linux components will simply build and run on your chip. Again, this is not as good as will be in x86 world or ARM world, but a huge majority of the things, 90% of the things will work. Again, not everything works with everything, and there is something that is called a fire marshal that helps put these workloads together. So, in summary, we will use Chipyard in the lab that was released yesterday to generate a minimalist RISC-V SoC for logic design and circuit experiments. So you can play with logic design, add your components, or you can take a component, its RTL, and make a circuit level experiments. There are people, for example, there are a lot of papers that are doing, say, in-memory compute for matrix operations. That's a totally valid project, to take something that is the RTL and replace it with a memory that does compute. We'll find out how well, by doing a project like that, you'll find out how well does that work. Our labs will exercise different components of a design flow. We don't expect everybody to exercise the entire design flow all the time in their project. But think of it as just as an opportunity. Pick something that you are interested in. For example, a project can test a circuit idea in the context of a larger system. Or design a block to improve the functionality of the SoC. And the three instructors here are more than welcome to discuss it, different options with you. In the next few lectures, we are going to do, there are a few things that we are going to do. We are going to have 2 language lectures. On Tuesday, we're going to talk about Chisel. On Thursday, we are going to talk about system Verilog. It's kind of decoupled from other things that we are talking about, but we know that we are not covering system Verilog in 151, and it does come up in interviews and in practice, so we are going to have a system Verilog lecture. We may add, we are looking for a guest lecturer. Unfortunately, our local resident expert, Sanjit Seshia, is teaching in the exact same slot, so he can't do the formal and different verification lectures, but we're looking for someone else to cover the verification after that. So if you have system Verilog and you have the basis of verification, you understand how does the verification work. And then after that, we're going to walk through a couple of components that are of interest of educational and research importance, like the tile link and the connectivity on the chip, and also how do we design networks on the chip and crossbars. So that's what's going to be happening for the next 2 weeks. After that, we are going to make an abrupt change and dive down into the technology, and then we're going to build up from the technology up to designing a whole thing. Oh, okay. Any questions here? With that, I will wrap it up here. I'll give myself 5 minutes break. I have an office hours. Please stop by, but I'll try to keep this office hour a little bit shorter and make up a bit later because I do need my voice. Thank you all.